In this video we will prove the Poincare inequality in one dimension. What is a Poincare inequality? Poincare inequality is one of the most celebrated inequalities in analysis. It means the following, that the L2 norm of the function u supported on the interval 0, 1 is bounded by a constant times the L2 norm of its derivative, where the constant here, it should be equal to 1. So step number 1, we can write u of x in modulus. So the absolute value of u of x is the integral from 0 to x u prime dp because of the fundamental theorem of calculus. And then we can use the triangle inequality to bound this. And then we can use the Cauchy-Schwarz inequality. So that integral over there is the square root of x times u prime, the norm of that in L2, 0x. That's the first part, so I take u of x equals the integrals from 0 to x u prime dp, so p is between 0 and x. Then I use the triangle type inequality and then here I use the Schwarz-Cauchy inequality. And I have that the function in absolute value is bounded by the square root of x times the norm of the derivative, the L2 norm, 0x. Okay, so now let's take u, that one, let's take the supremum in 0, 1, so that is the supremum of the function u, where x belongs to the interval 0, 1, to the open interval. And this can be bounded by the L1 norm of the function. So I have u prime dx, and this can be bounded by, so I can use the Cauchy-Schwarz inequality as well. So that one gives me just u prime L2 0, 1. So the infinity norm of u at 0, 1 is bounded by the derivative, by the norm of the derivative in L2 of 0, 1. So it's bounded by that. So here we have a bound for the infinity norm of the function u. And then we have the u L2 0, 1 squared is the integral from 0 to 1 u squared dx, and this is bounded by the integral from 0 to 1 u L infinity 0, 1 squared dx. This can be we can take this outside the integral, u L infinity 0, 1 squared integral from 0 to 1 dx, and basically that's u L infinity 0, 1 squared. And we have showed that the infinity norm is bounded, so this one is bounded by u prime L2 0 1 squared, and from here it follows that the norm of u in L2 0 1 is bounded by its derivative, by the norm of the derivative L2 0 1, or this can be written as the norm of u bounded by a constant times the norm of the derivative, where see here the constant is 1, and that's the end of the proof. So let's recap the steps. First, we use the fundamental theorem of calculus. We have the absolute value of the function u, and that's the integral from 0 to x u prime. We use the triangle type inequality, so it's going to be the integral from 0 to x, the absolute value of the derivative. And then we use the Cauchy-Schwarz inequality, and we obtain the product of these two terms, square root of x times the L2 norm of the derivative of the function. Then we work out the bound for the infinity norm. So the infinity norm is the supremum of the absolute value of the function in the interval 0 1. Then I know that this is bounded by the L1 norm of the derivative of the function. I can obtain this bound, and then I can obtain this bound using the Cauchy-Schwarz inequality. So I have that the L infinity is bounded by the derivative of the norm of the derivative of the function, and then I have a last step where I have the bound for the norm of u in L2, which is bounded by this integral here, and then working out this, I get that this is bounded by the infinity norm, and then I obtain that this is bounded by the L2 norm of the derivative of the function squared. And it's obvious that after that I take the square roots, and I have that at the left hand side of the inequality the norm of u bounded by the norm of the derivative of the function, and I obtain that the norm of u in L2 supported in the interval 0 1 is bounded by a constant times the norm of the derivative of the function u in L2, and here the constant c is equal to 1.